Imagine someone drops 30 student grade cards on your desk, and your only job is to find the single highest math score. Humans are notoriously bad at this. We scan the pile randomly, our focus drifts, and we eventually lose track of which cards we've actually checked. To guarantee an accurate answer, you have to switch to computational thinking. You replace intuition with a rigid, mechanical process, a series of repeatable steps that removes the possibility of human error. This starts by dividing your workspace into two strict zones. Every single grade card begins in the unseen pile. Once you check a card, it moves to the seen pile. Moving a piece of data from an unseen state to a seen state is the foundation of data science. It ensures every piece of information is processed exactly once, with nothing skipped and nothing repeated. This flowchart visualizes an iterator. It picks a card from the unseen pile, examines it, and moves it to the seen pile, repeating until empty. To answer questions, systems track observations using a variable. To count students, we start at 0 and increment each loop. We can upgrade this basic counter into an accumulator. Instead of adding 1, an accumulator variable takes the actual math score from the current card and adds it to a running total. Combining a repeating engine with a dynamic memory allows us to quantify massive datasets that would overwhelm any person's ability to remember. Total scores are a start, but data science often requires specificity, like finding the average marks for only the female students. This requires the ability to selectively ignore data. We achieve this by adding a filter. Before updating, the system checks a condition. Unmatched cards are bypassed. Compound conditions refine our search further. Using and or logic, the system isolates cards where the gender is female and the city is Chennai. This process relies on clear data types. A computer treats a name as a text string and a grade as a number. If a filter tries to perform a math equation on a word, the entire procedure will fail. This is how we find the top score. We use a dynamic filter. The variable starts at 0, and every time the iterator finds a higher score, the condition updates its own threshold to match that new high. Filtering turns a passive count into a targeted search, stripping away noise to isolate the exact answer hidden in the pile. When logic becomes this complex, visual flowcharts eventually become unreadable. To keep the process manageable, we translate the diagrams into raw text. This text is called pseudocode. Packaging these instructions into procedures with specific parameters makes the logic reusable, allowing us to apply the same rules to entirely different datasets. Some questions require more than one pass. To compare an individual student against the class average, we run a sequenced iteration, one full loop to calculate the average, and a second loop to perform the comparison. Ranking every student in the deck creates a massive scaling problem. It forces us to take one student's card and compare it against every other card in the stack. This is a nested iteration, a loop inside a loop. For 30 cards, that's 30 comparisons per card, resulting in an exploding complexity that requires significantly more time to resolve. As datasets grow into the millions, computer science shifts toward the challenge of efficiency. An algorithm is only useful if it can complete its task before the complexity of the calculation overwhelms the hardware. This is the algorithmic assembly line. Iterate to move it, use a variable to remember it, a filter to isolate it, and a procedure to package the logic for reuse. This rigorous framework is the foundation taught at institutions like the Indian Institutes of Technology to manage the systems running our modern world. The stack of 30 grade cards we used is just a starting point. Whether you are sorting school records or processing 30 million global shopping bills, the underlying logic is identical. These concepts provide the bridge between human intuition and machine execution. They offer the structural framework needed to take a complex problem and break it down into instructions a computer can actually follow.